Hello guys and welcome to another video. In this video, we'll be exploring redundancy or over constraint in mechanical systems. It is a very interesting concept and also a very important concept when we are designing mechanical systems, and especially if you want to design mechanical systems for precision. So what is redundancy? What is over constraint? To understand this concept, first we need to understand the concepts of degrees of freedom and kinematic pairs. So these are fundamental concepts of kinematics for mechanical engineers, which we study in college. The degrees of freedom are basically the number of ways in which a part can move or rotate. So let's say for an aircraft, it has 6 degrees of freedom. It can move forward, back, up, down, sideways, and roll, yaw, or pitch. So these are 6 degrees of freedom. So any object in space has 6 degrees of freedom. For machines, for example, this gantry, let's say for example, if you take a 3D printer, the 3D printer has a gantry, that print head can move X, Y, and Z direction. So there are 3 degrees of freedom. And the joints which allow us to constrain the degrees of freedom are these. These are called kinematic pairs. They can be fixed joints for a structure. For example, in a building, all the joints are fixed. They have rigid connection, there is no relative movement. Whereas for systems which require relative movement, for example in engines, there are bearings, there are pin joints in mechanisms, these are pin or revolute joints. Then there are prismatic or slider joints in which there is reciprocal motion with relative to each other. And then there are spherical joints, for example ball joints in suspensions. These allow rotation, relative rotation in more than one axis. So this is a fundamental concept in kinematics of mechanical systems. Now, what is redundancy? We can understand redundancy with a very simple example of a 3-link structure or a 3-link system. So for example, let's say there are 3 links and these 3 links are connected with 3 pin joints as shown over here. Now, this is a structure. This will not move. This is not supposed to move. It is not a mechanism. When you add one more link, it becomes a mechanism. That is when you, instead of connecting over here, you add one more link which becomes a 4-bar link mechanism, and then when you apply force, it will move. So this is a structure. This is the fundamental description of a structure. 3 links which are connected to with 3 pin joints is a structure, and which is the least required constraint for making a structure. Now when you add another link like this, let's say if you are adding a link over here, you're connecting it with pin joints at top and over here. This link, although it helps in bearing the load, the additional load, it takes up the load, it will add redundancy to the system. This redundancy, otherwise called as over constraint, shows up when we are trying to assemble this kind of a part. So let's say if we want to assemble this kind of a structure. So we place this, and then we try to assemble this. We have to fasten this and this simultaneously. It becomes difficult. Whereas the assembly of the structure on the left hand side is much more easier. Hence, redundancy and over constraint generally complicates the assembly process because of the over constraints, and also adds weight, adds parts, but is also necessary to bear the loads. For example, if you take flange couplings, these flange couplings connect 2 shafts. Now the flange couplings can be just having a single keyhole and they can connect the 2 shafts, but why are they having so many bolts or fasteners which are there? That is because it should basically withstand the loads, withstand the stresses, and that is essential for its functioning. Now in terms of the kinematic connection of the 2 shafts, you don't require these many bolts. Hence these bolts, although they are necessary, but they are redundant in terms of the constraints. Fasteners generally add redundancies, they add over constraints. Similarly, the same case is with welding. Welding adds redundancy and over constraint. Of course, it is very necessary for structures, for example, chassis frames or the body system of a car. For that, the whole thing has to be welded together for it to have integrity. In that case, redundancy is useful. But in cases where assembly is important and the loads are not that high, then redundancy becomes a disadvantage. A very good example of where over constraint or redundancy can be problematic for the design is the comparison between the fixed beam and the simply supported beam. So fixed beams are fixed at both the ends. Because of that, the stress concentrations will be higher at the ends when the load is applied at the center, whereas in simply supported beams the load distribution is generally better. Beams which are supported on either end with pin joints or knife edges as shown are much better as compared to fixed beams which are fixed at both the ends. But of course, because of certain advantages of fixed beams, that is the deformation is lower, for those advantages the fixed beam is generally applied in structures, and it's also more simpler in construction, whereas simply supported beams are more complicated in their construction because of the additional joints. But in terms of their kinematics, the simply supported beam is much better. So in machine design, generally where we can have a simply supported beam as opposed to a fixed beam, we should always go with the simply supported beam where the load distribution is generally more uniform. So of course it depends on how the beam is fixed to the columns, and it also depends on how the simply supported beam is supported using pin joints. There can be many different variations and the outcomes can vary. But in terms of the ideal or in terms of the theoretical concept of a fixed beam and a simply supported beam, a simply supported beam is not as redundant. It does not have over constraint as compared to a fixed beam. You can see redundancy playing out in furniture design as well. You can see stools. The stools which are having 3 legs are much more stable as compared to stools which are having 4 legs as shown over here. So the minimum points of contact for stability is 3. When there are more points of contact, then instability can occur. Because of the tolerances, the length of the legs will not always be the same, and because the length of the legs cannot be the same for all the 4, there will only be 3 points of contact and there will be instability.